Here's a question. When you flip a switch and a light turns on, what's actually happening? What is electricity really? It all starts with atoms. Every atom has a nucleus of positively charged protons with negatively charged electrons orbiting around them. And electricity, at its core, is just the movement of electrons from one atom to the next. Some materials make that movement easy. We call them conductors. Copper is the classic example. Others block electron flow almost completely. We call those insulators: rubber, glass, plastic. So the difference between a wire and the coating around it comes down to one thing: whether electrons can move freely. Now, electrons don't move on their own. They need a push. That push is voltage. Voltage is the electrical pressure difference between 2 points, the potential difference. Think of a water tower. The higher the water level in the tower, the greater the pressure at the pipe below. Voltage works the same way. A battery creates a voltage difference between its positive and negative terminals. One side has an excess of electrons, the other a shortage, and that difference pushes electrons through any wire you connect between them. We measure voltage in volts, named after Alessandro Volta. If voltage is the pressure, then current is the actual flow. Current, measured in amperes or amps, is the amount of electric charge moving through a wire each second. Back to the water analogy. If voltage is the water pressure, current is how much water is flowing through the hose. More pressure, more flow. But here's a twist that trips up almost everyone. We define current as flowing from positive to negative, called conventional current, even though the actual electrons are moving the opposite direction, from negative to positive. The math works either way, as long as you're consistent. So if voltage pushes and current flows, what stops it from just pouring through? That's resistance. Resistance is a material's tendency to oppose the flow of current, measured in ohms, using the Greek letter omega. Going back to the hose analogy one more time, voltage is the pressure, current is the flow rate, and resistance is the width of the hose. A wide hose gives low resistance, lots of flow. A narrow hose, high resistance, much less flow. That's why different components in a circuit do different jobs. They're just offering different amounts of resistance. Here's the most important relationship in all of electronics. It's called Ohm's law, and it's beautifully simple. Voltage equals current times resistance. V equals I times R. This one formula connects all three quantities. If you know any two, you can calculate the third. Here's what it means in practice. If you increase the voltage and keep the resistance the same, the current goes up. Makes sense. More pressure, more flow. But if you increase the resistance while keeping the voltage the same, the current goes down. A narrower hose, same pressure, less flow. That's Ohm's law. Everything else in electronics builds on this. One more useful piece: power. Power is the rate at which electrical energy does work, measured in watts. It's just voltage times current. P equals V times I. Now, how do you actually measure these things? With a multimeter. To measure voltage, you place the probes in parallel, across the component. To measure current, you break the circuit and place the meter in series. The current flows through it. A quick note on the type of electricity: direct current, or DC, flows in one direction like from a battery. Alternating current, or AC, switches direction like what comes out of your wall socket. One last practical tip: if you're building your first circuit on a breadboard, always use a resistor with an LED. Without one, the LED will draw too much current and burn out in seconds. Ohm's law tells you exactly what resistor value you need.